So chapter 4, we've got the homework already up there. We will be finishing chapter 4 today and probably starting chapter 5 and starting to look at some of the hopefully more simple chemistry with our alkenes without getting into too much detail, but we'll see what happens. Nomenclature, figure I'd put it back up there. Remember, you need to circle the longest carbon chain that contains the double bond, and that's because at this point alkenes are our highest priority functional group. So when we're trying to find or name our compound, we want to name it based on the highest priority group. Okay? So it doesn't matter what the longest individual chain is. If there's a shorter chain that has the alkene, that's where we identify as our main chain. Okay? Then the ene ending, all that fun stuff. Okay? Where we ended was looking at cis-trans naming, and I said that we're going to take it a step further, and we're going to look at E and Z nomenclature as well. Okay? So the cis and trans system really only allows us to compare two individual groups. So when we looked at rings, okay, we could say cis and trans when we had two different things attached. So we look right in the middle. If we did a wedge and a dash, we could say those two groups were trans to each other. Okay? But what happens if I add another wedge? Okay, can I refer to cis and trans anymore to name this cyclohexene in the middle, or cyclohexane in the middle? No. Okay, cis and trans only refers to two groups. As soon as I add a third, what would I have to shift to name this compound, to identify the arrangement of those groups? A trickier question. What was that? So we could number where they're at, but how do I specify their arrangement? That this methyl is up, this one's up, and that one's back. What was that? Z and E actually will only work for double bonds, but not a bad idea. R and S. You would have to go through and specify the stereochemistry about each of those carbons and specify R and S characteristics. Okay? Which is a bit obnoxious, but that's what you've got to have to go through and do. Okay? And because it's obnoxious, of course, for this class, we won't do it. Or maybe we will, just to be fun. I'm kidding. Maybe. So let's go through and circle our longest carbon chain on that lower left. Here we said we'd go back to this one as far as identifying it. So we'd go through and circle where our main chain is. We want to circle where our double bonds are, so we would circle this as our branch, not including, or not, sorry, and not this option. Both of those give you the same number, or no, they don't give you the same number of carbons. Never mind, there is only one answer. I can't count today, apparently. There we go. There's our main chain. Okay, how many carbons do we have in the main chain? We've got 6, so we're looking at a hex. Okay, what's our functional group? Ene. How many of those are there? 2. So this one's a little bit tricky, or added a couple extra wrinkles to this. Okay, there are 2 double bonds, which means we have to name 2 double bonds. So we could call this hexene ene. Well, that seems a bit silly. So what do we do instead? No, we'll go to di, just like we would have done with methyl groups. So when we named, none of these had multiple methyls. But when we had other structures where we had multiple methyl groups, we would go dimethyl, trimethyl, tetramethyl, all that fun stuff. We're doing the same thing here. We now need to specify that there's 2 double bonds, so we'll call it a diene. Where do we put that di? Right in the middle. How would you guess that? You would have thought, oops, except I just did an eraser. Hex diene. Okay? We've got an extra problem with this. Where are the double bonds? We need to specify where they're located. Okay? So So we could go through and number these out. We're looking at position 1. If we go left to right, at position 2 or position 4. The other direction, position 2 or position 4. So either way we number it, we're going to get the same thing. So we could just stick with 2, 4. Hexadiene. Okay. What are our substituents? We've got the bromo and an ethyl. We need to add numbers to these. What numbers do we give them? Give them 2 and 3, the 2 applying to the bromo. Why do I number right to left? Gives me the lowest numbers. Okay? And we could go through and now refer to this compound as 2 bromo, 3 ethyl, 2, 4 hexadiene. Okay? We've got an extra issue though. Can this compound do cis-trans isomerism? Okay, so to figure out if we have cis-trans isomerism, we have to evaluate both double bonds. Okay, so now that we've got a name, let's see, do I want to erase it? I'm going to erase some of it. Okay, I don't care about the substituents anymore. And we'll go back to our 2 rules. We'll start with green for our first rule and red for our second. So green, we want to cut the double bond perpendicular. So we'll cut in half, and we want to go through and then star important groups on either end. Okay, how many things are attached on the left-hand side of that double bond? I guess there's a couple different answers you can give me here. What's the lowest number you could give me? Less than 4, greater than 0. 2. Why is it 2? Don't forget the hydrogen. So now when we compare across our double bond, and now I'll go ahead and switch to the red, we're looking at hydrogen versus carbon. Which one has the higher atomic number? Carbon. Which one should be starred? Carbon. We can shift to the right-hand side of our double bond. How many things are attached to the double bond? 2. Show that implied hydrogen. This is an interesting point. You'll notice how I'm drawing the hydrogens. I'm showing a relatively sharp angle up. Okay. Let me go ahead and show it in a different color so it stands. Like I said, the name wasn't all that important, right? I have seen students go through and show something like this. Okay. Is that right or wrong? As far as this class is concerned, I don't really care. That's fine. Okay. As far as trying to decide priorities, that's going to be a bit of a difficult location. Okay. Because our next rule is to go through and cut our structure in half parallel to the double bond. Well, if I happen to star the hydrogen, where's the hydrogen? Above or below? Okay, so that's really difficult to figure it out. Okay, so why am I drawing the hydrogens up? Okay, or on that kind of that sharp of an angle? So it's not quite above and below the plane. Why is the pen not working? There it goes. What's the hybridization of that central carbon? sp2, which means what bond angle? 120. Okay, I've got it shown where that angle is as close to 120 as possible. If we draw the hydrogen on the other direction, does that look like 120 degrees? Or even that? Okay, it doesn't accurately reflect the three-dimensional structure. Okay, so when we draw out our structures, we want to try and be as accurate as possible to the three-dimensional structure because that will help us answer questions. Okay, it's not something, for better or worse, that I'm going to take off points for, but I do want you to be trying and to draw them out as accurately as you can. Okay, so if we go back to the topic at hand, we're comparing hydrogen to carbon. Which one has the higher atomic number? Carbon. We can star that, go through, assign cis-trans, or decide are stars on the same side of that red line or on opposite sides. Same side, we can refer to that as a cis double bond. Our cis strands, because we're only comparing two groups, let's go back and evaluate. If we look at our double bond, we've got two hydrogens. The only things that we're looking at arranging are two groups. We can refer to this double bond according to our cis trans nomenclature, if we so chose. Okay? If we decided to get crazy with it, instead of calling it cis, we could refer to it as Z. Okay? How can we tweak our name to reflect that? Well, way out at the very, very front of the name, so let's say this was all the stuff, crap, junk in there. Okay? Way out at the beginning of the name, we would say at position, what do we say that was, 4? Okay, this is our 4 double bond, because we numbered left to, or right to left. At position 4, what's the arrangement of the atoms around the double bond? It's Z, 4, whoa! Sound effects, nice. 4Z. Okay? And we could put parentheses around that. Because we have that double bond at position 2, we'd also have to go through and specify it so we can start to predict that we're going to have that 2 and some extra information about it. Okay? Does that make sense? Lowest to highest again. Okay? Very similar to what we would have done with stereochemistry, R and S. Okay? If we had multiple stereocenters, we shifted that information way out to the front of the name because it helped organize and condense that information. Okay? If we move to the next double bond, so now I'm going to erase all our stars and lines and hydrogens and fun stuff. Okay, let's move to our next double bond. Again, our first rule is cut the double bond perpendicular, so we'll cut it directly in half, and then start to compare things. Carbon versus carbon. Is there a difference in molecular weight? Or atomic number, sorry. No, so what do? We move to the next atom. Okay? We could kind of cheat with this one by just going out to the next atom all the way through, and we would star which one, top or bottom? Top, okay, because we could go through and just looking at the sigma structure, we've got 3 carbons versus 2, so it would be carbon-carbon, no difference, carbon-carbon, no difference. Next atom out would be hydrogen-carbon. This carbon takes precedence, and we could star all the way back. While that technically, or I guess not technically worked, maybe it is technically worked, that's not strictly correct. We should have seen that difference a lot earlier. We shouldn't have to go all the way through the chain. Why? The double bond. Okay? That double bond must be treated like it has a phantom carbon on both sides. We can then compare carbon versus carbon, no difference. Carbon versus carbon, no difference. Carbon versus hydrogen, is there a difference? Yeah, we can star. Okay? So that was one of those harder rules when it came back to deciding these. Remember, in general, the lower the hybridization, the higher the priority. Okay? If we move to the right, well, sorry, questions on that? That's good. Right-hand side. We want to evaluate here. Carbon versus bromine. Which one has the higher atomic number? Bromine, so we go ahead and star that. Now that we've got both sides starred, we can cut our double bond in half, parallel to the double bond. Where are the stars? Opposite sides of our double bond. So if I wanted to compare them strictly to each other, I could say trans. When we move to nomenclature, we're not picking specifically 2 groups. We have to assume that that trans applies to the whole structure. Okay? We can't do that anymore. That double bond, okay, is first off different from the other one, but then second off, it also has 4 different things attached to it. Okay? So we have more than 2 things to compare to each other. This means we must shift to our EZ nomenclature. Okay? If you would decide that the relationship is trans between those, what do we end up referring to it as? E. Okay? So we go back to our name, and we would start off with 2E, 4Z. What did I say it was? Then 2 bromo, 3 ethyl, 2 4 hexadiene. Might even be hexadiene, but spelling. Don't worry about that. Okay? Kind of makes sense? Yes, no? What?
I see why you don't like naming now.
And just to be obnoxious, we can go ahead and erase that, and we'll say, as far as naming, what have we looked at? We've looked at 1, 2, 3 of 11 possible things to evaluate. And those are just the 11 we're covering this semester. Okay? There's all sorts of other functional groups. Okay? Questions about any of that as far as the E and Z goes? It is fairly straightforward. You're just trying to come up with those comparisons. You do have to remember now, instead of looking at just cis and trans, we're also bringing in this EZ nomenclature. So you got to make sure that those are tied appropriately to each other. Okay? When it comes to nomenclature, the problems that I've assigned in the textbook will potentially throw in common names. So the common names from the alkanes or the alkenes or the alkynes. I don't expect you to have those memorized for the lecture exams. I do expect you to take advantage of the textbook and look them back up and say, oh, sec-butyl was this group. That must mean I can apply this back to this structure. Okay? So I do expect you to be using the textbook to make reference to those names. Does that make sense? Okay. Couple extra mnemonic devices that I probably will never repeat to help you kind of remember. Cis was ultimately we had things on the same side of our double bond. Okay, so you can think if you were German, I guess it's German, they're on the same Seite. Okay, Z and same. It gets worse. This one I'm definitely not repeating, but multiple students have said it enough that people have remembered it. Trying to remember trans with E is not the easiest, but for some reason, I don't know why it works for people, but you can think tran E. Okay, I don't know why, but people seem to think it works. Okay, so as long as you remember that when you're looking at trans, it's E, and Z is cis, I don't care how you remember it, and I'll give you as many mnemonic devices as I can that are not ultimately too offensive. Okay, as best I can. Okay. So now what we're going to do is look at kind of the alkene-alkyne repercussions when we're looking ultimately at the pi bond. It's not so much the alkene or the alkyne themselves, it's that pi bond that prevents this. So if we take a look at an alkene, okay, I meant to actually draw on the sigma structure here. If we looked at, what do we have here? Pentene, it looks like. 2, 3, 4. Okay. If we looked at pentene, we looked at from that side, and we kind of just turned the molecule a little bit, our CH3 down here would be coming out at you, so we get the wedge. Okay, and our ethyl, if we did the rotation where we pulled this up and out, would then be going the back, and we would see that being dashed going away. Okay, the reason we do that rotation is so that we can better see that p orbital. Okay, we're doing a bunch of rotations on this one, but it's kind of the point on seeing this. Okay, if we then compare that across to what's happening on the other side, what does that double bond look like if we look at our sigma structure? Okay, so if we compare our double bonds, what we've got is the cis or Z conformation versus the trans or E conformation. So what we're trying to do is decide, is it possible to rotate around the double bond to interconvert between the cis and the trans? Okay? When we look at it from the side, it doesn't seem all that obvious. So what we're going to do is now look at it as a Newman projection from the end. Okay? So when we look at it from the end, our CH3 in the case of the trans would be coming up on our right-hand side. So you can see the CH3 shifting kind of a little bit down towards the right. The only reason these are kind of staggered, kind of X-wing factor away from each other is because, any ideas? If we take a look at, let me highlight now in green, all three of those bonds occupy what space? It's the bond angle between them, 120 degrees. Our geometry is trigonal planar. They're all in the exact same plane. If we turn and look at the structure from the end, why are those two atoms not in the same plane? So that we can see it. That's all it is. Okay, so I'm just tweaking them off axis a little bit so that we can see those bonds a little bit cleaner. Otherwise, they overlap with the bonds in behind, and it's going to become impossible to see. Okay, so realize that these are all in the exact same plane. Okay, all we've done is shift them a little bit so they're more visible. Okay, so our CH3 would come up on our right. If we take a look at our ethyl, it would come up on the left-hand side. If we take a look at our cis conformation, our ethyl and our methyl end up being on the same side of our double bond. Okay, see the relationships? Which of those should be more stable, our cis or our trans? The trans, why? Our two largest groups with the most electron density are as far away from each other as possible. And the cis, they're occupying the exact same plane. Okay, so this image shows us that a little bit better. Okay, and the process of trying to interconvert between the trans and the cis, what we have to be able to do is to rotate about the double bond. Okay, and that's what this arrow is trying to show. We're now rotating about that. So if I try and rotate by 90 degrees, that front atom, just turn it by 90 degrees. The CH3 now aims down, a hydrogen up. What happens to the p orbital? It must also rotate. Is that p orbital now parallel to the p orbital and back? No, it's perpendicular. So what I did was took an overlapping stable interaction, and now I said, you know what, I don't like it, I'm going to get rid of it. Okay, is that a very likely thing to do? No, I'm starting in something nice and low energy, and now I'm shifting to full-on p orbitals that aren't stabilizing each other. So I've gone from two p orbitals that kind of stabilize and interact with each other to reduce their energy, to now shifting to two p orbitals that aren't interacting with each other. I drastically shoot up in energy. Is that rotation a good thing to do? No. Okay, which is the primary reason that we don't see rotation when we look at our pi bonds. Okay, both with our alkenes and to a lesser extent with the alkynes. The alkynes you won't get rotation either, but it's irrelevant for the alkyne. Why? The bond angle is 180 degrees. If we did a rotation about that bond, we wouldn't be able to tell the difference anyway. Okay? Kind of makes sense? Okay. This will come into play a little bit when we look at products of reactions and stuff like that. Okay? So we don't get any rotation about individual pi bonds. Let's go ahead and take a look at some molecular formulas. I'm not a big fan of mathematics, but this actually brings in some mathematics, so I'll try and do it as best I can, do it some kind of justice. Make my parents proud. They're mathematicians. Okay, so take a look at a molecular formula for our alkane, simplest alkane. What do we have? Told you formulas were bad, so now you've all forgotten about formulas. But give me a molecular formula for the alkane. How about for the next one? For the next one. So let's see how many of you are mathematically inclined in this. Anybody notice a pattern between those? Could we potentially come up with a way to simplify our formula so that it applies to all alkanes, regardless of our structure? What do I mean by that? If I give you a carbon and say n number of carbons, how many hydrogens would I have if I've got an alkane? So 2n, not a bad place to start. So let's compare that back. See, methane. What's n in methane? 1. According to my formula, what would I get? How many hydrogens should I have? 2. How many hydrogens do I have? 4. So is this formula good? No. What do I need to do? Add 2. What? Oh. I'm not going to draw out all those formulas again. Okay, so for a standard alkane, all alkanes will follow this same overall format. CnH2n plus 2. Every single alkane will follow that overall general format. If we add in heteroatoms, what are heteroatoms? Anything that's not hydrogen or carbon is a heteroatom. Okay? That's going to change our overall formula. We can still have alkanes with heteroatoms in them, but our formula picks up some weird connotations. Okay? So we're not going to worry about that because this gives me enough of a mind meld as it is. I don't want to have to worry about other stuff. Okay? So we'll keep it relatively simple when we're looking at this. When we move to the alkenes, so first off, our simplest alkene is going to have to be ethene. Why ethene? Why can I not get any simpler than that? I have to have at least 2 carbons to have a double bond. Okay? So what's our formula there? C2H4. How about propene? Lower left. How about cumulene or propdiene? Okay, that one's a little bit trickier to look at, but can you see a pattern showing up with your alkenes? What's that? Every double bond is a loss of 2 hydrogens. So if we look at an overall alkene, okay, just a mono-substituted, let's say single alkene, our formula becomes CnH2n. Okay? So when we looked at our ethene, N was 2, so hydrogens need to be 4. 2 times 2 gives us our 4. Okay? What happens as we add more double bonds to our overall structure, though? As we continue to add double bonds, we continue to lose hydrogens. Okay, so we can start to propagate this into a different arrangement or a different series of formulas. Okay, and so someone, like I said, mathematically inclined, looked at these patterns and was able to come up with some different systems. So if we look at saturated alkanes, so completely saturated the carbons, they're all sp3 hybridized, okay, and no rings. Okay, we'll talk about rings here in a second. Our formula for a saturated alkane is that CnH2n plus 2. Okay? As soon as we make our structure unsaturated, meaning we've removed some hydrogens, so you can evaluate saturation as the number of hydrogens. So if I unhydrogen the structure, just turned hydrogen into a verb, okay, I lose 2 hydrogens for every type of unsaturation unit I can generate. We just looked at one, pi bonds. Okay, the presence of a pi bond removes 2 hydrogens. So what we can do is now look at a new formula, and we get CnH2n minus 2x. Wait, I added an extra little thing here. What's that minus 2x? The formula that we had before was what? What did I say it was for alkenes? I had CnH2n. But what did I say? That formula was only applicable for only one double bond, or a single alkene. Or what? Single alkene. There we go. Okay. This X is our degrees of unsaturation. A degree of unsaturation is equal to a double bond or a ring. Okay? So if I only have 1 degree of unsaturation, so we'll add that information, a double bond or ring, X becomes, with only 1, X becomes 1, and I get 2N minus 2, which is exactly that formula. Okay? So given a formula, we can start to interpret some information about its characteristics. We could look at it and say, oh, that's a saturated alkane. Or, oh, that is an unsaturated structure. So it probably has some double bonds or triple bonds or even rings. Okay? Kind of makes sense? So that's all we're ultimately trying to get at there, is figure out what that X is. So we're trying to dissolve or determine some extra information. Okay? What about rings? Why does rings do anything? Let's go back to the propane structure. We looked at propane. We got CH3, we got 2 hydrogens, another CH3. What was our formula? C3H8. If I want to generate a ring, the smallest ring I can get effectively is a triple bond. Okay, so what do I have to do to make that extra bond between those 2 carbons? Because if I just make that bond, I now have how many bonds to those carbons? 5, so I have too many bonds. What do I have to do? I have to remove some hydrogens. There's the C2. What does the formula become? C3H6, which is our equivalent here, where our degree of unsaturation in this case is 1 ring, so we get 1 degree of unsaturation. N was 3, so 2 times 3 minus 2 gives us 2 times 3. Shoot, this is what happens with formulas. I hate formulas. 2 times 3, 6. Oh. Because it's a change from our alkane. Sorry. It's a change from our alkane. So this 2x is changing our overall formula for our alkane. So we have to include the plus 2. Sorry. Now it's fixed. Okay. So when we go through and do our degrees of unsaturation, we count it out, we do get our correct formula there. Sorry about that. You guys see that? Okay. So a ring is the same, or results in the same type of thing as a double bond. Okay. Does it make sense? Why would a ring give you the same kind of result as a double bond? Okay. They're effectively the same thing. Okay, a ring is 2 carbons bound to each other, right? In kind of a cyclic structure. So let's take 2 carbons and let's bond them to each other a second time. There's a ring, right? It's a really odd looking ring, but if we kind of compress it and look down small enough, that does look like a ring. Those 2 carbons are connected twice to each other. Okay? So we do have a ring structure when we're looking at double bonds. We just typically don't see it that way. We look at it more as a double bond, as that straight kind of bond. Does that make sense? Okay, so let's go through a couple examples here. Now that we got the formula set up right, we should be able to solve these. We just looked at all of the names, so let's take a look at some formulas. If I give you C3H6, that's cheating, we've already done that one. Let's do C5H12. How many degrees of unsaturation? So how do we figure that out? So now we end up going in the reverse. Okay. I always have, and there's another formula that you can memorize for this too, but I never memorized it, so I have to derive it each time. Okay. If the structure was fully saturated, how many hydrogens would I have? What's N? 5. So 2N is 10 plus 2 is 12. How many degrees of unsaturation are in this compound? 0. We can't possibly have any. We're already saturated. It matches our saturated formula. Okay. We'll come back to this one in a second because we're going to add some extra mathematics to it and prove that this still holds true. So let's go through and try another one. Let's do C6H6. Okay. If it was fully saturated, how many hydrogens should I have? 14. Just checking your math. Okay. Do I have 14? No. Okay, so it's not fully saturated. Now I want to figure out how many degrees of unsaturation there are within that. Anybody do the degrees? You get 4. So what do you end up doing to get that? Take 14, which is our fully saturated, minus what we've already got in our structure, 6. Then what? Then divide by 2. Why do we divide by 2? What's that? Not quite. Oh, I see what you guys are doing. You're solving for x. You can do that. A degree of unsaturation was the loss of how many hydrogens? 2. So if we're going to count our degrees of unsaturation, just divide by 2. Okay? What's our answer here? We get 4. Okay, or for those of you like me that are a little bit slower, it'll be 8 divided by 2, which gives us 4. These are too fast.
So the question would ask for what are the degrees of saturation?
What are the degrees of unsaturation? Yep. Okay, we could then make it even more complicated. We could make it a multiple choice. How many double bonds are in the structure? What was your answer?
You don't know.
You don't know. How do you not know? Because it could also be a ring. Okay? So if I get 4 degrees of unsaturation, that is possible that I have 4 double bonds. It's also possible I have 3 double bonds and 1 ring. It's also possible it's 2 double bonds and 2 rings. Or it's 4 rings. Okay? So it gives us some information about our structure, but it doesn't give us our structure. It allows us to kind of eliminate and simplify some things. Does that make sense? Okay, if we took that back to our original formula that I said I wanted to go back to, though it sounds like you guys are already better at this than I ever was. What did I say, C5H12? We said our saturated was 12. If we go to the formula or the calculation that we just did, our degrees of unsaturation was how much was fully saturated minus, we'll call it our test, divided by 2. If it's fully saturated, it's 12. We're testing that formula, which was how many hydrogens? 12 divided by 2. What do we get? We still get 0. Okay? So if you're trying to find the degrees of unsaturation within a compound, evaluate how many hydrogens would be there if it was fully saturated. Once you've got that number, minus how many hydrogens are in your formula, divide the whole thing by 2, and you've got your degrees of unsaturation. Okay? Make sense? Okay. So let's go ahead and move on unless we have questions. Okay. don't mean to go backwards. Let's go forwards. Last thing I want to talk about within Chapter 4, there's only a small section on it. It takes up a couple pages within the chapter. And because it's kind of biologically relevant, we'll talk about it. Or nutritionally relevant, and a lot of people seem to be doing stuff related to those fields. Isoprenes end up being one of the more important biological compounds available within nature. Okay? And it's because that basic unit can show up multiple times in multiple different ways in larger structures. Does anybody recognize any of these structures? Let's see, can I cheat? Dang it. I didn't even write my answers on the board. Last one? What do you mean last one? Bottom right? Like, bottom right? I mean bottom left? Yeah. That is cholesterol. Anybody recognize any others? About the bottom right? You guys don't know, right? No one has even a guess? Okay, good. So you can't challenge me. Pretty sure that one's retinol. Okay. What is that one? What's that compound used in? Oh, interesting. It's your eyes. Your eyes use retinol to detect light. Okay. What's happening? You're doing a cis-trans isomerism about the double bonds within that compound. That isomerism, or that change in the structure, turns into a signal that our brain interprets as a particular color. Okay? So retinol is pretty important. Apparently it's used in face creams too. Okay? How about the top one? No nutrition majors? Oh. Nutrition majors want to raise their hand and embarrass themselves if they don't know it? Again, beta carotene. And that last one, pretty sure. Because of the stereochemistry, it changes the compound. Limonene. You guys know how to spell it, right? Then good. That's it? Oh, you remember? Okay. We've got limonene. You'll be isolating limonene in lab on Monday. Okay. Why was that one tricky for me? If we turn that into a wedge at the bottom there, what's the compound become? Is it the same thing? No? What's the relationship between those two? I can draw it out so you can see it a little bit better. Not that you could see it much better. The way I draw things. What's the relationship between them? You're right, it's coming back to RNS. For it to be a diastereomer, we'd have to have two stereocenters. So we have enantiomers. This compound is pinene. That's an N in there. Okay. So pinene smells like pines. What does limonene smell like? Limes. What did we do? We changed one orientation. We went from a dash to a wedge, and now we recognize that as by an entirely different smell. Okay? So very simple changes in structure turn into very vast changes in what we can acknowledge and respond to. Okay? All that's beside the point. Let's get back to our isoprenes and terpenes. Okay? So isoprenes make up all of these compounds. Okay? So one of the things that I'm going to hold you responsible for is being able to identify the isoprenes within each of these compounds. So you should be able to tell me how many isoprene units make each of these. It's a bit of a challenge, so let's pick the easy one first. Let's start with limonene. Where do you guys want to start trying to find your isoprene unit? You'll notice, I'll mention this too, you'll notice there's a difference with double bonds. I don't show any double bonds in the isoprene, and that's because it kind of depends on the reactivity of the overall isoprene on where the double bonds end up showing up. I believe technically our isoprene, it's an eraser, has 2 double bonds, okay, at the head and the tail. That allows reactivity at both of those double bonds. We'll look at, actually we won't look at that reactivity, so ignore that.
So when you're looking for it, you want to go through the double bonds?
You don't want to focus on the double bonds because as they react, if I react over here, how many bonds would that carbon now have at the end? If I form an extra bond. 5, so I have to break a bond. What's the easiest bond to break? The pi bond, so it shifts into here, but now how many bonds does that carbon have? 5, so this bond shifts out and reacts with something else. So tracking the double bond is not going to be the easiest way to solve this. What you need to do is look for some other pattern within the isoprene unit that you think will be easier to find. What's the easier thing for you to see? I'll tell you what I would see. What's that group? Fishtail, also known as the iso group. So what you can do is look for the iso part and hope you can kind of fish or figure it out from there. So if we take a look at limonene, I see an iso group right there at the bottom. Okay, that's the easiest one for me to see. Okay, yes, there's other isoprenes within it, so we could find those. So fishtail's up. Now I can either go left or right. Which direction do I want to go? I don't know. Pick one and see what happens. So go left. Sorry, did you say left first or right? You just switched it on me, didn't you? Okay. So there's an isoprene unit. We've got 5 carbons. 1, 2, 3, 4, and 5. Okay. That isoprene unit will have to connect to another isoprene unit. Okay, so let's show that bond in green. So there's a bond connecting it out. So where's the new isoprene unit start? That next carbon. What do we have right there? What shape is that? There's my iso. There's my next isoprene unit. Where does it connect? Right there. Okay. So how many isoprenes are within that? We get 2. Okay. Let's go through and do retinol just because it's a little bit smaller and I don't want to deal with the other ones. Where do you want to start with retinol? Okay, in the ring. Where in the ring? Okay, let's pick that iso group. Where do we go, left or right? Okay, I'm going to go right first for a particular reason. So we've got 1, 2, 3, 4. Oh, actually, 5. That does actually fit, doesn't it? Let's say we went down the other direction, though. And then we went down, said that was our isoprene. I do have the 5 carbons for the isoprene, but then what happens with this carbon or these pieces? Where did those come from? Who knows? Those don't really match an isoprene. Okay, so that choice was a bad choice. Let's try a different one. We could try and go out that direction and see if we could connect with our isoprenes. Next one. Hey, that kind of worked. How about the other direction? Do we have an isoprene there? No, we don't have the iso group. So while that sort of worked, that didn't quite work out for us. So what does that mean? Sorry, I should have warned you. Our initial choice was wrong. We should go this direction. There are isoprenes. Okay, so there's 2 types of questions that I could ask on an exam. You could get how many isoprenes made up the structure. So in this case, you could just get away with, what is that, 1, 2, 3, 4 isoprenes. Or I could be particularly mean and change the question to circle the isoprene units that make up this structure. Okay? More than likely on an exam, I would ask both questions. Okay? So you could guess at a number and hopefully get it right. Okay? And then you would still lose points for not being able to identify where the isoprenes are, but that's a more advanced question. So it's an easier question followed by an advanced question. I try and mix both of them in there. Okay? Make sense? Okay, that is the end of chapter 4. So overall, easier, harder? Seems pretty straightforward, right? Not too bad. Okay, so let's move on to chapter 5. Okay, chapter 5 is looking at reactivity. Okay, so it's going to get a lot more difficult when we deal with, or not a lot more difficult, but we're going to start to look at reactions of alkenes. How do they react? How can we make them? Or not how can we make them? How can we react them? How do we make alkenes? We've already talked about that. How do you make an alkene? You need to take hydrogen away, yeah. But that's not it. We could try and eliminate a hydrogen molecule, but we haven't dealt with a reaction or a reagent that does that yet. And we won't deal with one that removes 2 hydrogen atoms from a molecule. What reaction makes alkenes? I know this is now 2 weeks ago. That's an elimination. Your elimination reactions make alkenes. You can make an alkene from an alkyl halide. And in the process of the elimination, you lose the halide. It acts as a leaving group, and a base or heat comes along and removes the hydrogen, allowing you to form the double bond. Okay? So we've already seen how to synthesize them. Now what we're going to look at is how to react them. I've got one question on energy diagrams. We've done a little bit with energy diagrams, right? Not a whole lot. Okay. I'm not going to test on energy diagrams, but I do want at least a homework question on it, so that's why that's there. I will look for that specific question or an energy diagram drawing question if you don't have the textbook in your homework. Okay, so I absolutely want you to do that and have some exposure to energy diagrams. Okay. The rest of it, we're looking at a new type of reaction, which means we'll look at a new type of mechanism. You've got the addition reactions. We'll follow that up with some redox chemistry. We'll look at some synthesis, which is now going to bring in, once we get to those synthesis questions, you're looking at all the information from this chapter, from chapter 5, looking at alkenes, reactivity, and then also substitution and eliminations. Okay? So it's going to start applying and mixing everything together. Okay? And then the last part is just more problems on reactions. So let's compare our alkanes versus our alkenes. Okay? When you compare those two, we do end up increasing the reactivity. Why do we increase the reactivity? We've got the pi bonds. Those pi bonds are held further, or the pi electrons are held further away from the atoms. They're more accessible. They're a source of electrons. Those can come out and react. So when you see an alkene, you should immediately be looking at it as a source of electrons. What types of reactions, or what types of, what reactant classification can we give to a source of electrons? You may have been saying it. What did you say? No, not quite. We won't do SN2 with alkenes because of sterics. What kind of things act as a source of electrons? Bases, like Bronsted bases, or Lewis bases, or say maybe like nucleophiles. I know it's in blue. It may be hard to see, but the answers are already up there. Okay. Sometimes I ask questions where the answers are there. Sometimes not. Okay? So when you see an alkene, those are the immediate reactivities that you should be thinking about. Okay? So if you've got a base, what's the best thing to react with that base? Acids. Okay? So what we're going to look at as far as reactivities with our alkenes is reacting them with acids. Those acids are going to be our primary reaction. These are going to be the biggest ones that you're responsible for. So what we can go through and do is pick a good acid here. In this case, I'm going to pick HBr. Okay? So we could go through just based on what we started talking about and starting picking out mechanisms. Okay? Or what we could do is say our understanding of is a little bit shaky with mechanisms and our reactivity of alkenes. And instead what we want to do is find positives and negatives. Okay? It's foreign chemistry to us right now, so let's try and simplify it. We're going to pull a face test. Alkene versus HBr. Anybody give me the name of HBr? Hydrobromic acid. I think you were about to mouth the next thing. It's a strong acid. So which would you be more concerned about being splashed in your face? The alkene or HBr? HBr. What makes you nervous about HBr? It's a strong acid. What part of it makes it the acid? The hydrogen. What charge is the hydrogen? Positive. So what we've got is a very positive hydrogen and a very negative bromide. Okay? So what we found is some source of reactivity within these two molecules. Okay? If we still no idea how to react, we could then go through and pick one of those. Okay? Because somehow or another they've got to react. So let's say the bromide. Bromide's negative, so what do I need to find? Positive. So I could go to the alkene and say, do I have something positive? Okay? I think I saw you saying hydrogen. Is that right? What are the hydrogens bound to? Carbons. What's the difference in electronegativity? None. So the hydrogens aren't really positive. Okay, well how about the carbons? Maybe the carbons are positive. What are the carbons bound to? Carbons and hydrogens. What's the difference in electronegativity? None. Okay? So we don't really have a positive within the alkene. Okay, which is what we just mentioned. We said there isn't really a positive, it's a source of electrons. Okay? So just by guessing at it and saying we know HBr, let's see what we can work with. We tried the bromide first, didn't work out for us. Okay? So now we can shift over to the H+. Okay? So it's positive, what do I need to find? A negative. So I go back to my structure and say, where do I have something negative? The electrons, or electrons need to be, we need to find electrons, let's try that, somewhere within the structure. Where do we have electrons in this structure? We've got them in the pi bond and what kind of bond? Sigma bonds. So we've got electrons in the sigma versus the pi bonds. Which one of those is more accessible? The pi bond. So what we're going to do is take the electrons in that pi bond and share them with that hydrogen. Okay, so we can start off our mechanism. I like red, why not? We'll start our arrow at the source of electrons, which is our pi bond. You'll notice that's in the middle of the structure, and we share those electrons with the hydrogen. How many bonds would hydrogen then have? Too many, so what do we have to do? Break a bond. The bond we'll end up breaking is the HBr bond, and those electrons will move towards the bromine. Why should they move towards the bromine? Why does it like the electrons? It's more electronegative than the hydrogen. Okay, one extra thing I want to add here, those charges that I wrote up there should be more appropriately shown with the partial symbols because those are ultimately partial charges. Okay? So, what's the result? Did we do anything to this carbon? No. How about that carbon? That carbon? Interesting. I didn't do anything to the carbons. So let's draw out the CH3. Yeah, we'll just leave it at that. Hydrogen, hydrogen. Didn't do anything to that hydrogen. And I shared electrons from the pi bond with the hydrogen. Okay, Okay, well, if I share electrons, what am I doing? Making a bond. Well, the electrons started from the pi bond, so let's just say we do that. You know, it's a bond between the atom and the bond. Okay, does that work? No. Okay, so we have to decide, does that hydrogen have a particular spot to go to? It's going to have to be bonded between the hydrogen and carbon. Which carbon? This one? Whoops, that's an eraser. Our CH3? No, why not? Octet's full. Okay, between the other two. At this point, both of them have unsatisfied octets. We could put that hydrogen on either one. Which one's preferred? Okay, those of you actually giving me an answer, do you actually know the answer, or are you just guessing? Sort of both. Okay, I can kind of accept that. We'll assume the rest of you said you don't want to put it on the right one, you want to put it on the left one. So we'll go through and add that hydrogen. I had it drawn as a blue. We'll go ahead and put the blue hydrogen on, the right one. We have the other option, putting it on the left one. So we get two possible products in quotes. Why do I say products in quotes? Doesn't really true. There's another big reason. Are these products yet? Why are they not products? Good. Our octets aren't satisfied. Okay, if our octets aren't satisfied, what should we be suspicious of? Right? Why would it react again, though? Bromide's negative. What does bromide need to react with? Positive. I don't see any positives. What are we missing? Ends with an F. 2 words. Formal charge. Okay? How do we know that? We can take a look at our products. What's our overall charge on our products? What do we see? What's the charge on this structure? Do you see a charge? No, so it's neutral. What's the charge on this one? Charge on this one? Negative. What's the charge on our reactants? This one is. What's this one? What's this one? Neutral. So if we compare reactants to products, I went from a neutral state to a negative state. That's not allowed. Okay, I created charge. We can't create charge, which means when I drew out my products, I missed something. That missed is the formal charge. Okay, so we can use formal charge, comparing reactants to products, to help us identify that something is missing. What is that formal charge that's missing? It's a positive charge. Where's the positive charge located? The carbon that's missing its octet. So the one that didn't get the hydrogen. Okay. Is the positive charge stable? No. So what could happen? Or what does it need to have? Electrons. Do we have a source of electrons? Where's that source of electrons? The bromide. So we could either have the bromide attack that one or this one. What's the result? I get that product or I get this product. Are they the same thing? No. So this brings up a dilemma. Two possible products. The only way I'm allowed to get two products is if everything between the process of making those products is of equal energies. Okay? So that means we have to go back to our two intermediates, or our intermediate step here, and decide, is there a difference between these two paths? The bromide's the same in both cases. The only difference is where that positive charge is located. Okay? So let's classify the positive charge in both cases. For the top one, what would you classify that positive charge as? What's that? What does that mean? Okay. How many carbons are attached to the carbon with the positive charge? 1, 2. So I would classify that as secondary. What about the bottom one? How would I classify that carbocation? Primary. Is there a difference in energy between a primary and secondary carbocation? Yes. Which one is more stable? The secondary carbocation. Which one does not form according to our rules that we memorized from SN1 chemistry? Primary. Which of these products is not formed? The bottom one is not formed. We only see our top product. Okay? So what we went through and did was derive a result for our product. Okay? Which is a lot harder than I would expect on an exam. Okay? On an exam, I would tell you reactants and products, give me the mechanism to get there. Okay? Here we went from beginning to nothing and we're able to get a product. Okay? And we even went through and found out our best product. Okay? And that's a we. You guys did help, right? That wasn't just me. Okay? How do you guys feel about that chemistry? Not too bad, hopefully. Okay. So we could look at it broken down. We've got it actually drawn out now where it's all computerized. You could go through and add our mechanistic arrows. I think I heard a so.
So I have a question. So what was that actually, what substitution were you doing?
So as far as classifying the reaction, what
Yeah.
type of reaction? So is it a substitution? So when we decide our mechanisms, so a substitution, we compare reactant to product. Is this a product in the middle? No, it's intermediate. We don't care about that. So what we're comparing is our reactant to the very end, or in this case, reactants. Okay? How many reactants did I start with? 2. How many products did I end with? Only 1. What did I do? Okay, if I eliminated, I removed something from one of these. What did I remove to make these? Okay, and the double bond was never removed. It may have shifted around and the electron density is in a different spot, but I never removed the double bond. What's that? What did I remove a hydrogen from? Took it off the bromine, but then I put it on this.
So you just substitute.
So, but what did I substitute? Okay, I know it's difficult to try and piece it together. In a substitution, we strictly swap one thing for another. So when a substitution reaction occurred, I started with 2 and I ended with 2. When I did an elimination reaction, what happened in the elimination reaction? I started with 1 and I ended with 2. Okay? The structure with the double bond and whatever was removed or eliminated from the organic molecule. What happened here? Does it really fit either of those? No, we've got a new type of reaction. We took 2 molecules and we added them together to make 1. We've got an addition reaction.
But the same rules apply as far as the secondary, primary.
Because of the intermediates that are formed, yes. Okay?
I had a different reason why I picked the top one.
Yes.
Just because of the Terpenes carbon. More likely to go inside.
So works. Okay. Questions? More questions on that? Just kind of want to see what the next slide is before I decide that we're completely done. Okay. Oh, just looking at this. So deciding between our products, we could look at cation stabilities. The other thing that we could look at was anion stability. How can we look at anion stability? I didn't see a negative charge. Can I do a resonance structure for this? fact, I can get two. I can show a resonance structure where I put a negative charge at the end and the positive there, or I can show a resonance structure, negative there, positive there. Let's do it in different colors so they stand out. If we do red, we can, eraser. Or between these two possible resonance structures, which one's more likely? Blue or red? You should know the answer already, because the red, because we put the positive charge on our secondary. So we could compare between this. Positive charge on a secondary versus positive charge on the primary. Which one's more stable? Secondary. So it makes sense for red to be our favorite. Well, let's take a look at the anion. Maybe the anion messes with things. Negative charge on a primary versus negative charge on a secondary. Which one was more stable? Primary. Both point to red being our most reactive position. Okay? So we could evaluate putting the, drawing out both products and evaluating which product generates the more stable carbocation, or we could look at the resonance structure and decide which resonance structure actually makes the most sense to react from. Okay? So when we draw out our mechanism from the beginning, we could have said, it's going to be a bad idea to use blue. The double bond goes out to attack our HBr. Or what we could have done is drawn out our resonance structure first, and then said that negative charge goes out and attacks the HBr. Both end up being valid. One way might be easier for you to see than the other. Okay? Kind of makes sense? I'll just kind of push the rest of that slide because the rest of the slide just says which one's more stable. Okay? So our tertiary cations are more stable. Our zeroary or primary anions are more stable. Okay? And it all has to do with the different charges. What makes them each more or less reactive? Okay? Any questions?